Love this podcast? Support it and sponsor today. Simply head to ozcastnetwork.com for details.
Thank you for downloading and listening to This Pathological Life. If you're interested in continuing the story, we have a second series called This Medical Life. Please download it and subscribe now.
Dr. Travis Brown, why do we need a podcast called This Pathological Life?
Every disease has its own story to tell. So we're going to tell them.
I went for a routine checkup, did some blood work. A little while later, I had a phone call. Your white cell count's actually off the chart, is what he said. Those were his exact words. Things are not right. I'm going to send you to a specialist the next town over. So I went over there, and he told me what he thought was going on. He thought he said you either have some type of a tumor or CML, and I think it's CML. I'll never forget talking to the doctor, and he said, well, you're going to need this bone marrow aspiration. That's one way I can really tell what's going on. And I'll never forget he was turning away from me. And I said, Doc, is this going to kill me? And he just looked at me and goes, I don't know yet.
In this episode of This Pathological Life, we're looking at chronic myeloid leukemia. And Dr. Travis, this is where I admit some ignorance. I didn't know there were many variations of leukemia. What is it that has made you focus on this one?
There are lots of variations of leukemia. It's not until you study them that you realise how many there are. So the reason why I've chosen this one is because it's quite an amazing story. Right at the moment, cancer treatment for a lot of different cancers is sort of it's becoming better, but in the past it's been a broad spectrum kind of kill dividing cells, and because cancer is dividing the most, it will be most affected, but other parts of the body also get affected, so there's lots of side effects. The amazing thing that we'll find about chronic myeloid leukemia is we started to get targeted therapy. You'll hear a lot talked about personalized medicine. So we're actually starting to sort of say, not only do we have a tumor here, but what's almost its molecular signatures that we can target to specifically inhibit the growth of the tumor, but not affect other healthy tissue. And so you will get less side effects. And this is the quintessentially diagnosis that uses that targeted therapy and sees what the possibility of the future lies ahead. So our story starts in 1839 when in Paris a 44-year-old female was admitted to hospital and ended up dying of an unknown illness. There was a French physician there by the name of Alfred Don who wrote a report on her blood film the day after her death.
More than half of the cells were mucous globules. The fact needs perhaps some explanation. You know that normal blood contains 3 types of cells. Red cells, the essential cellular constituent of the blood, white cells or mucous cells, which I consider as being secreted from the vascular wall, and the small globules. It's the second variety which dominates so much that one wonders, knowing nothing about the clinical course, whether this blood does not contain pus. As you know, the pus cell cannot yet be differentiated with definite accuracy from mucous cells.
So this report and this case was collected by Alfred Don, and he ended up publishing a series of these in 1844. But the next case we see is in 1841, and this is from an Edinburgh physician by the name of Dr. Craigie. Now, he admitted a 30-year-old patient to the Royal Infirmary. He was a male, and the patient ended up dying there as well. Again, an unknown illness, and the blood was examined on autopsy. And what they noted was this purulent matter. So that's, again, pus, and lymph had mixed with the blood and gotten circulated. So they're saying, well, here's cells that shouldn't be in the blood, and a lot are in the blood. And so it's a curiosity, but it was noted and reported. And then we have in 1845 a Scottish physician by the name of Dr. John Bennett admitted a 28-year-old male who presented with unwellness but a very enlarged spleen. And he wrote,
"He is of dark complexion, usually healthy and temperate. 20 months ago, he was affected with a great listlessness on exertion, which has continued to this time. In June last, he noticed a tumour in the left side of his abdomen, which has gradually increased in size till 4 months since, when it became stationary."
So he was treated at the time with the best therapy then, which was leeches, so bloodletting, purging, which was vomiting and laxatives, as well as potassium iodide. Now, the patient's condition appeared to improve and he was discharged, but he was readmitted 3 months later. And the symptoms that he was readmitted with was fevers, he had issues with bleeding, he had these sudden fits of abdominal pain, which initially had time between and then increased in frequency. And then he had tumours developing in his armpits and his groin and his neck. And he ended up dying. An autopsy was performed a few weeks later, and the patient's blood was noted to be full of pus, of these white cells. And Dr. Bennett wrote an article, and he called it a case of hypertrophy of the spleen and liver, in which death took place from suppuration of the blood. Now, this suppuration is effectively inflammation, but he wrote in that article,
"The following case seems to me particularly valuable, as it will serve to demonstrate the existence of true pus formed universally within the vascular system."
So during the autopsy, they didn't find any source of the pus. Now, it's important to note that there was not a link at this time to microorganisms and infection. They knew about sepsis, and they knew there was a reason the white blood cells should be there, but they didn't have that link. And so the interpretation was somehow the blood had become suppurative or purulent on its own. This was a case of inflammation of the blood. And then in the same year, we have Rudolf Virchow, and he published a case report of a woman who was 50 years old, and she presented with a very large spleen. She had a history of 4 years of ill health. She had this swollen abdomen and ended up dying 4 months later. Now, Dr. Virchow noted on this patient they had in their blood markedly overgrowth of white blood cells. Her spleen was dense and pulpy, and she had a thick milky layer of white cells floating above the red cells. Now, what we would call that today is a buffy coat. So when you get a EDTA with red blood cells in it, there's a little white layer of white cells, which is normally very small. What he was noting is that was actually really large, so lots of white cells in there. Now, Virchow knew of Bennett's case, but he disagreed with the conclusion. He didn't think it was a suppuration of the blood, but he couldn't find any other cause for the white cells or the increased splenomegaly. And so what the two sort of deviated a little bit, but in the same direction. Bennett thought it was he called it a leukocythemia, a white cell blood. But Virchow called it initially a visus blunt, which means interpreted as a white blood. But he changed it a few years later in 1847 to the name of leukemia, which leukos means white and emia means blood. So this is where we get the first term, leukemia, being used. Now, we started to get increased cases being reported because now it's known as a condition. But again, no one knew of the cause of this leukemia. And it wasn't until 1868 when we start to get investigations happening as to where blood comes from. And we have a report from Ernst Newman reported that changes in the bone marrow were linked as the source of blood and a continual process of production of bloods that would go out into the circulation. He also noted that red blood cells had an ancestral cell, a stem cell, what we would call these days. At the same time, we have Giulio Bezero, wrote in an article that red blood cells come from nucleated red blood cells in the bone marrow, and also suggesting that white blood cells come from the bone marrow. Now, this was pretty revolutionary at the time, and it wasn't accepted until about 20 years later, in which case we find in 1900, the Swiss hematologist Nageli described the myeloid cell lineage. So when we're talking about myeloid, we're talking about the cells in the blood that have granules in them. So that's things like neutrophils, basophils, eosinophils. They all come from the same ancestor. So what Nageli described was that these have blast cells, and these blast cells are the primitive cells from which the lines come from. And he noted there was a myeloblast and there was a lymphoblast. And then in 1913, we start to get the monocytic leukemia discovered, and therefore we have myeloblasts. So in all of this, we're still just starting to learn about the blood and how it comes together. Chromosomes and inheritance in the cell is also starting to be discovered in the late 1800s. But these chromosomes at the time of discovery, their nature and function was unclear. So when we go back and look, we find the father of genetics, the Austrian monk Gregor Mendel. Now he performed a simple, well-controlled, beautifully designed genetics test using peas. And they're following through generation to generation, and ended up finding the principles of inheritance. He's the one that coined the term dominant and recessive, and ended up able to do the statistical analysis to predict inheritance. He ended up presenting his groundbreaking study to the Brunn Society for Natural Science. However, no one recognized its significance. And it wasn't until late 1800s when German pathologists observed gross mitotic abnormalities in tissue sections that they started to realize that this may be linked to tumor development. Enter in 1910 and we get the American geneticist Thomas Hunt Morgan, who did pioneering studies on the Drosophila fly, and he noted that male fruit flies had red eyes, but every once in a while you would have a male fruit fly with white eyes. And an experiment remarkably similar to Mendel, except for with the flies, again, a pattern of inheritance was established. Theodore Boveri had a hypothesis that mammalian tumours may be initiated by mitotic abnormalities. The cell dividing, if it was abnormal, could cause a tumour. However, it would take decades for this theory to be borne out, because the techniques were not good enough. In 1921, it was announced that humans have 48 chromosomes, and this was accepted as fact, but they don't. They have 46, and it wasn't until 1955 to 1956 that that fact was borne out. And then we enter in with Peter Nowell and David Hungerford, and in 1956, Peter Nowell joined the faculty of the University of Pennsylvania to study chromosomes in leukemic cells. Now, they had done previous studies and not identified any chromosomal abnormalities in tumours. And they looked at acute myeloid leukemia, so AML, but there was no consistent genetic abnormality found. However, when they looked at chronic myeloid leukemia, CML, they found they had 2 patients and they had the same changes. Both of them had a small chromosome 22. They ended up reporting a series of 7 patients with the same disease, all having the same abnormality. Now, in accordance with the Committee for Standards for Chromosomes, the abnormality was named after the city it was discovered in, and it was called the Philadelphia chromosome. But the problem was left. Where had the head or this segment of chromosome 22 gone? No one knew.
In true this pathological lifestyle, you've left us with the cliffhanger to end this first part, Travis. And yet again, we see that intrepid researchers along the way and physicians notice something, can't explain it, but they just keep building upon the insights of those from before. Let's have a look at the genesis of the first moves to come up with a drug in just a moment.
Best memory I have of this drug was very early on in clinical trials. So we took a woman who went off of her medications for leukemia, and her white count went from 25,000 to 125,000 in a week. We started her on Gleevec, and I was pretty worried because if her white count went up at that rate, she'd be in trouble very quickly. 3 days later, her white count was 122,000. A week later, it was 89,000. 3 weeks later, it was normal. And so this is a woman, nothing was working. Her white count would explode off treatment. And in 3 weeks, it was normal on Gleevec. And I knew that at that point, we had something that nobody had seen before in terms of the ability to control this leukemia.
Travers, let's continue this exploration of CML. And you did pose something before the break that I'd like us to wrap up now. What happened to chromosome 22? Where did it go?
The Philadelphia chromosome was discovered in 1959, but it wasn't until 1973 that we found where it went. And this was discovered by Dr. Jeanette Rowley, who was a hematologist from Chicago. And she studied a whole bunch of photographs of patients' chromosomes who had CML. And what she ended up finding was that the head of chromosome 22 had attached onto the tail of chromosome 9. It had switched. Now, we didn't have words for this because, again, this is new discovery. This ended up being called a translocation. It went from what we call now a T1922. And the bottom of 9 ended up going on the head of 22. In 1982, the Dutch researchers in Amsterdam found the gene that was on chromosome 9, and they called it ABL. In 1984, American researchers in Maryland found what the gene was on chromosome 22, and they called it BCR. So therefore, the translocation that occurs in CML is now called BCR-ABL. Now, normal cells tightly regulate signals for cells to divide, not divide. And they call these kinases. Kinases are described as molecular master switches that turn pathways on and off. And this is for cells to grow, to divide, to stop dividing, and even to die. However, when we get the translocation of 9 and 22, this tightly regulated signaling system is bypassed, and effectively the master switch for the cell is always turned on. So we have unregulated, accelerated kinase signal to the cell to proliferate. This is now what we call an oncogene. This BCR-ABL is a gene that is able to convert a normal cell into a cancer cell. So we now know where the head of 22 went, and it switched with 9. And we know the effect is that this causes uncontrolled proliferation of these white cells, these granulocytes. And these granulocytes become much more prevalent in bone marrow, in the spleen, and in the blood. So what can be done about it? Well, that was the next question. In the late 1980s, we had Nick Leiden, who was with the Dana-Farber Cancer Institute, and they had a collection of kinase-specific inhibitors. Now, Nick met with Dr. Brian Drucker, who was an oncology fellow at the time, and he was interested in these kinase inhibitors for this BCR-ABL. Now, Nick had been involved in creating all of these inhibitors that was now owned by a company called Cyber-Geigy. And what Dr. Drucker tried to organize is to test some of these kinase inhibitors. But because they were actually owned by a different company, and with Nick's company and then with Dr. Drucker, the agreement ended up falling apart and they weren't able to get any agreement for a trial to go ahead. In 1993, Dr. Drucker went to Oregon Health and Science University and then recontacted Nick Leiden, and he had been informed by Nick that Ciba Geigy had even synthesized a larger collection of these kinase inhibitors. And one was of particular interest. It was named CGP 57148. And he thought that this would be highly selective for this BCR-ABL mutation. So Dr. Drucker went and was able to get an agreement with the university, and 2 weeks later, a small collection of these kinase inhibitors arrived. You'll end up hearing us refer to a drug called Gleevec. So instead of that CGP name, this drug ended up being called Gleevec. And right at this point of time in the early 90s, CML was a fatal disease. It didn't respond to traditional chemotherapy drugs. It had a very poor response. It was a disease that took a few years, but it would end up dying for most people with the disease. There was some treatment, but like interferon alpha, but this was poorly tolerated because it had lots of side effects. The only cure was a stem cell transplant, but only a small percentage of people were eligible, and it had significant mortality and morbidity associated with it. The median survival of a patient, what we say pre-Gleevec, was around 3 to 5 years, and less than 15% of people survived beyond 8 years. So Dr. Drucker takes this drug and starts experimenting on it. So with the Petri dish with CML leukemic cells in it, he added the drug, and overnight the CML cells died. In another Petri dish, he took the bone marrow of a CML patient, ended up getting leukemia cells, clearly in the bone marrow, put the drug with it. Not only did the cells who had leukemia die, the normal cells were not affected.
Wow.
Then we have these cells implanted into a mouse and was treated with the drug, and the tumour regressed within days, and normal cells were unaffected. The results of this was published in Nature Medicine, and Dr. Drucker expected the organisation Ciba Geigy to be really excited, but they actually weren't. The company had gone through a few mergers and was now under a very large company called Novartis. But they assessed the economics behind it and realised a drug trial would cost between $100 and $200 million for a relatively rare cancer. A few thousand cases occurred in the US each year. And so I'll just divert a little bit and ask a question for you, Steve. What do you think the best drug that a pharmaceutical or a business can make? What's the best drug they can make for them as a business?
Well, one that you need to take daily, over and over again for the rest of your life, that's within a price point that you can afford, so it can become part of your regular grocery shopping, I would imagine.
Exactly. And so then conversely, aside from a drug that kills you, what's the worst drug that they can make?
Something that very few people ever need and is prohibitively expensive, that the countries that have pharmaceutical benefits scheme don't consider qualifying.
So in that area, almost the worst drug a business can make is a drug that you take once and you're cured for life. And so you don't need it again.
Oh.
So if you look at the economics behind that...
I hadn't thought of that aspect.
If you look at the economics behind that, let's say you want to do a drug trial for 100 people, and it's going to cost you $100 million. If it's a tablet that is taken once and they're cured, even if you price that tablet once it's done as $1 million per tablet, you'll have to have 101 patients before you make $1 million on that. And that's just business regarding it. And so Novartis is looking at this going, there's not that many patients we'll be able to treat. We're going to spend a lot of money developing this and probably not have a lot of people who would need it. Therefore, it doesn't make financial sense from their perspective. It ended up taking Dr. Drucker 3 years to convince Novartis that a drug trial was worthwhile. Again, then they changed the name to Gleevec, and they said, okay, go ahead with it. Now, his first patient was a volunteer who was a 60-year-old male. He was a retired train conductor, and he's from the Oregon coast. And this was the first time the drug was ever put into a human. All these experiments are exciting and encouraging, but you won't know until you actually experiment on a human that the side effect profile. And so he ended up giving the first dose, and Dr. Drucker waited by the bedside for the entire afternoon with this patient, but no side effects were found. There was no unexpected results. Ended up increasing the dose over time, and it was tolerated really well. By 1999, they had 54 patients on high-dose Gleevec, and 53 had had a complete response in days. The drug was continued for weeks and then months, and the drug was a raging success. There was a remarkable amount of people now alive today because of this drug. And there's an interesting quote that's attributed to Dr. Drucker that he had achieved the perfect inversion of the goals of cancer medicine because his drug had actually increased the prevalence of cancer in the world. And that's just because people were living now with cancer being completely controlled.
What a story. And that gives us the global perspective. Let's come back in a moment and let's focus on CML and Australia.
I have lots of different jobs, including directing a cancer center, running a lab, seeing patients, and also trying to raise a family. My history with blood-based cancer actually dates back to when I was a medical student, and I learned about the cure of childhood leukemia, some of which was supported by LLS-funded researchers. And what fascinated me about was you could take a uniformly fatal disease, often killing children within 6 weeks, and move within 20 to 30 years to a curable leukemia. And that was really what ignited my enthusiasm to pursue blood cancers.
For the last part of our episode on CML, I'd like to start, Travis, by really honing in on Australia and how common is chronic myeloid leukemia here in Oz?
So this is a rare cancer. It accounts for about 0.03% of all cancers. So we get, on average, a bit over 300 patients diagnosed each year. The majority of them, so over 70%, are over 40 years of age. So the median diagnosis for this disease is between the age of 40 and 60. You can get younger people. It tends to be very rare in children, and it tends to be a little bit more prevalent in males than females. So it tends to be almost sort of middle to older age in that category.
And looking at the natural history of CML, things like signs, symptoms, onset, etc., can you walk us through that?
Yeah, so the natural history and what we can see even from just the discussion previously is it tends to have a slow onset. So whilst those kinases are sort of always jammed on, the cells are proliferating, but it takes a while for those cells to end up filling bone marrow and spleen and the blood. So it tends to take a few years, and what ends up happening is initially, sometimes it can be even asymptomatically picked up, so people are feeling okay, and then they have a blood test and find a huge white cell count, which is unexpected. Sometimes, because of the disease progression, they'll have a bit of anemia, but they'll also tend to get a large spleen. So what we talk about is abdominal fullness. So these people will not have something to eat, but feel very full very quickly, and that's because the spleen sitting right next to the stomach is filling out in space, and you have less space in your stomach for food. So there's the generalized symptoms such as malaise and fatigue and weight loss, but only about 10% of them tend to get a large liver, so what we call hepatomegaly, and about 5 to 10% of patients have enlarged lymph nodes, lymphadenopathy. So it tends to be a slow onset, and you can get vague symptoms or maybe not even have symptoms at all.
And in that last segment, we talked about the Philadelphia gene. What numbers is that responsible when you're looking at cases of chronic myeloid leukemia?
So the majority are Philadelphia gene positive. 90% of cases are due to this translocation. That leaves about 10% which have complex cytogenetic arrangements. So there is a very characteristic appearance down the microscope of cells with all different kinds of lineage apparent. So it's quite a striking diagnosis. But sometimes if it comes back as Philadelphia chromosome sort of gene negative, then they'll have to go looking for other causes because it's very distinctive. So about 90% are Philadelphia chromosome positive gene mutation.
All right. Now, there are many phases to CML, 3 in particular. Can you walk us through them and give us that insight from your perspective?
Yes. So the majority, there are 3 phases. It's chronic, accelerated, and blastic. And the majority of people fit into the chronic phase. 90% of people are in this chronic phase. And that's considered a stable disease range. So they'll get a cell count and it will stay about that very high cell count. It's still very high. But what ends up happening is the cell just keep on dividing. But otherwise, there's not a whole bunch of other symptoms associated with what's going on. About 5% of people fit into the accelerated phase, and this is when we start to get increase in blasts of the cells. And if that's left untreated, it will tend into the last phase, blastic phase, within about 6 to 12 months. And this is where we get very high counts. And without treatment, the survival is less than 6 months. And that's where about 70% go down the myeloid blast origin, and the rest is into lymphoid blast origin. But the majority of people are in the chronic phase, where it seems to be stable disease. Particularly if they're treated, it will end up going into remission for this area.
Are some of us more predisposed to CML than others?
It is interesting. There's no familial association at all with this disease, and there's no associated with benzene or toxins. There is an associated with ionizing radiation. So this is things like nuclear accidents, atomic bomb type stuff, and radiation for ankylosing spondylitis or cervical cancer. But the peak incidence of this after exposure is about 5 to 10 years. Atomic bomb survivors have a median time for it to present after 6 years, but it's interesting. It's not seen in the survivors of the Chernobyl accident, so maybe it's a dose dependent, like heavy dose one, may predispose. But again, they're not other than those factors do we link to CML.
Okay. Now, what is the prognosis if we are sitting in front of one of our listeners, GP specialist, or a patient with CML? Can you give us your take?
So the comparison, if we look, again, discussing pre-Gleevec, what we've discussed before, the mortality rate for that patient before the treatment was 10% in the first 2 years. And then it went to 15 to 20% each year after that. So the median survival, even with sort of some of the newer therapies at the time, with hydroxyurea and interferon alpha, was about 3 to 7 years. And without stem cell transplant, they would succumb to the disease. Then we've got post-Gleevec. We have an annual mortality rate of 2% in the first 12 years. So that gives us a 10-year survival rate of approximately 90%. There are transformations, so the disease can transform into an acute leukemia, and that tends to occur in the first few years of the disease if it's going to with the treatment, but that occurs only in about 1 to 2% of the cases. The best prognostic sign is if the patient is able to get to complete remission within the end of 12 months. And so that comes to the end of this story as to chronic myeloid leukemia is a remarkable success story. It was once a fatal disease with limited treatment options, and now it's a survivable condition where the patient takes a tablet with minimal side effects, if any. It's essentially fallen now into a chronic disease category, even though it's a cancer, long-term disease. There are now second-generation drugs that I'm not going to discuss here. I'll leave that to the realm of hematologists about that. But this is a story and a testament to the power of research and persistence. And now a disease that was once fatal is now treatable and survivable.
Another triumph for evidence-based medicine and another fascinating story. Thank you, Dr. Travis Brown.
Thanks, Steve.
This Pathological Life is produced by ClinPath Pathology in South Australia. Episode notes, references and learning objectives, when applicable, can be found at thispathological.life.com.au. And you can contact the hosts on Twitter via @Dr. Travis Brown or @Steve Davis. Thanks again for listening, and just a reminder, if you haven't done it yet, have a quick search in your podcast app for our second series, This Medical Life. Dr. Travis Brown has rolled up some extra guests, some extra topics, and we continue the story there, and we'd love to have you along.
Love this podcast? Support it and sponsor today. Simply head to AuscastNetwork.com for details.